Well, so it is really a pleasure to have Eric Dunham here to give a talk. So Eric is a professor at Stanford. He was actually we kind of got him in town for another meeting earlier this week, and as part of that, convinced him to stay an extra day so that he could give the UTIG seminar. And I wanted to thank. I know a couple folks rearranged their time slots or days to give the UTIG seminar so that we could accommodate this talk. Eric is really well known for his work, and as you can tell from the title, modeling of earthquake processes. His background kind of extends beyond that, and if I take it back to the beginning, I guess. So he has actually a degree in BS in physics from the University of Virginia. I never like to share how old people are, so I'm not going to tell you the year of that. And then he got a PhD from UC Santa Barbara, also in physics. And there he worked with, among other folks, Ralph Archuleta, whom folks here may know as somebody sort of really influential rupture modeler and understanding the physics and energetics of earthquakes, and has been at Stanford since 2009. Is that right, Eric? As a faculty member there, and Eric is sort of at the forefront of the modeling community and bringing together geophysical observations, geological observations, and really complex numerical models of not just, right, so what he's going to talk about today is earthquake processes and some really cool things that happen when you introduce simple rules for complex behaviors like the introduction of fluids into that process. But he's also worked on much more computationally focused questions of just code development and benchmarking of codes, and he's worked on volcanic systems. And if you were to look at a list of some of the students and postdocs that have come out of his group, you'd probably recognize a lot of those names, and they're not all in the earthquake arena, but really pleased to have him here to talk about this today. And with that, I'll turn it over to Eric.
Thank you, Demian. Thank you all for coming this morning. So as Demian mentioned, I'm going to talk about the role of fluids and faulting and how we've introduced fluid transport, pore pressure dynamics, permeability dynamics into models of the earthquake cycle, and talk about some of the behavior that emerges from that. I want to highlight some of the co-authors here. So Ozawa is a postdoc who's been working with me for about a year now, and a lot of the work I'll present we've done together. Natalia is a new student who started over the summer. Yoon, Wei Chang, and Callie are former students now elsewhere. So I'll introduce you to faults. Faults are localized surfaces that accommodate most of the deformation between plates and sometimes within plates. In the upper brittle part of the crust, that deformation is brittle. Fracturing processes lead to fine-grained fault zones, and the sliding there is frictional. In the deeper part of faults, deformation, faults continue down into the lower crust and upper mantle, often as ductile shear zones or roots of faults. The focus of this talk is going to be on that very interesting transition from frictional to viscous and some of the processes that take place there. Fluids, I think, are really fundamental to understanding that behavior in many faults. And so that brings in processes like what are the dynamics of pore fluid pressure, what controls viscous flow. You get creep closure of pores that can, that compacts and pressurizes the fluids. So those are some of the processes we'll be looking at. In the seismogenic zone, as I mentioned, the deformation occurs via frictional sliding or shearing in localized fault surfaces. So we think a lot about the dynamics of the friction coefficient, but that's not the only thing that can influence fault strength. It's well known now, especially from induced seismicity, that changes in pore fluid pressure can also affect fault strength, right? So increases in pore pressure push back on the total normal stress compressing faults and making it easier to slip. So a lot of the dynamics I'll talk about today come from changes in pore fluid pressure. I use rate and state friction. It's a very widely used, but still somewhat empirical formulation. The main thing you need to understand is that friction coefficient evolves towards a velocity dependent steady state that can be either velocity weakening or velocity strengthening, depending on the sign of this A minus B parameter. So when A minus B is negative, it's velocity weakening. The faster you're sliding, the lower the friction coefficient. That is thought to be a necessary condition for unstable slip or for earthquake behavior. and for a while was thought to be a requisite condition also for slow slip events. I'll show you that I don't believe that that's true. The other possibility is velocity strengthening, right? The faster you slide, the higher the frictional resistance you encounter. Typically, that's thought of as promoting or only leading to aseismic slip, but I don't think that that's true. One of the most fundamental questions in geodynamics, broadly speaking, is understanding what's the distribution of stresses within Earth's lithosphere. And these ideas go way back into at least the 70s and 80s, and it's understood. This is a plot of differential stress, so a measure of deviatoric stress or shear stress, the differences from just some nominal lithostatic pressure. In the upper part here, where deformation is frictional or brittle, the strength is proportional to the effective stress. Those are thought to, or at least a common model is that those increase linearly with depth. At some depth, the temperatures become hot enough that the rocks themselves start to flow viscously, as I showed you before, and then there are viscous flow laws. They're all thermally activated, so the deeper you go, the higher temperature, the lower that flow stress is, right? And it's whatever the weaker deformation mechanism that it allows accommodates deformation. So a common model in the upper part here, right? The frictional strength and hence deviatoric stress levels depend on pore pressure. So you have to introduce a model for that. A very simple model. It's simple not because it's necessarily right, but because it has just one parameter, would be to state that it increases linearly with depth, just like lithostatic pressure does, and to introduce some factor lambda that controls how, that states how different that pore pressure is from the lithostatic gradient. So a hydrostatic model would have a lambda of 0.3 to 0.4, depending on what you choose for the rock density. There's no reason that it has to increase linearly with depth. I'll show you lots of models that give very different pore pressure distributions, but you can see the massive range of uncertainty there is in this calculation, or the huge dependence there is on pore pressure, right? If you have no pore pressure, that's the lambda equals 0. The hydrostatic case is the one shown here, twice hydrostatic, 2.5 times hydrostatic. It's massive. And if you look at the x-axis here, right, there's uncertainties that come from uncertainties in the strength of the lithosphere that come from uncertainties in pore pressure, and it's huge, hundreds of megapascals, right? So getting a constraint on pore pressure is of fundamental importance, right? This stress distribution controls how stresses are transmitted through faults, trigger-induced seismicity, all sorts of things. Fluids are also huge players in subduction zones, and so a lot of what I'll show today is relevant and driven by subduction zones. In subduction zones, the oceanic plate is traveling downwards through increasing pressures and temperatures. It undergoes dehydration reactions that release fluids. You can see in this geology schematic, there are fluid migration channels that are drawn. There's good geologic evidence that fluids are ascending along the fault and sometimes ascending up into the overriding plate. This is more of a geophysical view of things where we see within the seismogenic zone, there are patches that appear to, of higher coupling that slip in large earthquakes. And there's interesting transition to eventually steady aseismic sliding or shearing, but there's a transition region here where there is a phenomenon called slow slip event. I'll tell you more about those in a second. So I'm interested in pore pressure, and so to understand what controls pore pressure, we have to understand how much fluid is being produced and where it's migrating. So this is a calculation for subduction zones. So you can take a typical composition for the oceanic crust. This calculation just assumes standard mid-ocean ridge basalt ward composition, drives it or combines that, the thermodynamics of that composition with some thermal model coming from a geodynamics calculation. So you put those together and you can calculate what's the percent weight of water that's bound in the mineral structure. And as you go deeper, here, there are a number of dehydration reactions, right, that correspond to these steps or ramps in this plot of bound water. So that water is being liberated, it becomes pore water, and it's free to migrate. Where does it go? So in this calculation, we're going to assume that the upper 600 meters of the subducting plate are the fluid source, that those fluids ascend almost instantaneously, at least on geologic timescales, up to the plate interface. And then we're going to assume that they get channeled upwards. We're going to need to introduce some thickness of that fluid transport region. I tend to think of the place where the fault is slipping in large megathrust events or slow slip events, right, as a region of active permeability enhancement, right? So it's natural to think of it as a fluid transport channel, right? So then you take the fluids that are being released, you drive them upwards along the fault or this fluid transport zone. You can make it have variable width. And what comes out of that calculation is an estimate of the fluid flux. So this is known as a Darcy velocity. It's cubic meters of water being transported per unit surface area orthogonal to flow per time. And so the numbers that come out from in a typical subduction zone, right, it does of course depend on the width of this fluid channel, but they're in the range of 10 to the minus 11 to 10 to the minus 7 meters per second. To give you a sense of what that number means, it's almost exactly the same as annual rainfall in Austin, Texas, right? About a meter per year that you get, right? So it's not a huge amount of water. It's coming up fairly slowly, but as I'll show you, it makes has a profound impact on the dynamics of the system. This calculation assumes that all of that water continues up along the plate interface, but of course, it's also possible that it diverts from the plate interface and goes up into the overriding plate, right? And so then any place that happens, up dip from that, there would be a drop in fluid flux. And so I'll show you some models that explore the impact of that on the system behavior. So I'll come back to slow slip events. So this is one of the major focuses of our work. So slow slip events are commonly observed in many subduction zones, particularly the younger or warmer subduction zones. The subducting plate undergoes these dehydration reactions. They take place over a range of depths, but a lot of the dehydration reactions happen down here beneath the mantle wedge corner. Those fluids, as they ascend, they might come up into the overriding plate. They might come back up along the plate interface. But around and somewhat up dip of the mantle wedge corner in a lot of these subduction zones, instead of the fault just steadily creeping along during subduction, it is intermittently somewhat locked and then slips. It doesn't slip in a fast earthquake that produces a lot of seismic shaking. It slips over the course of days to weeks in slow slip events. These can be magnitude 6 or 7 events, but they're just extended in duration. They were first noted with the advent of geodesy. You can see it in these GPS stations on land, right? So, it's being pushed landward, the station is being pushed landward, and then there's a reversal of direction during these events. So this is an example from Cascadia. You can see that these slow slip events occur about on an annual basis. On seismometers, you can see tremor, right? It's sort of this high frequency noise that accompanies it and is thought to maybe be produced by lots of small low frequency earthquakes. We look on the right, the contours here are depth contours. The whitish dots are tremor. The color is showing the outline of slow slip, when a slow slip event, right? So you can see a lot of the slow slip is happening in a depth range between 30 and 40 kilometers, 30 and 50 kilometers. The tremor occurs within that and somewhat down dip of that. The geodetically locked portion of the subduction zone, that's where the big megathrust events are going to happen. That's indicated here. There's a lot of debate about how far down it goes. This map shows it going to 15 kilometers. Some people think it goes a little further. And there may or may not be this transition zone where there's partial coupling, whether or not a big megathrust event ruptures into the transition zone or even into the slow slip zone is really unknown. And it has huge implications for the kind of ground shaking and to some extent tsunami generation, right? So it has huge hazard implications to figure this out. There's a lot of models that implicate fluids in controlling slow slip events. This is just one model. Now this is showing another subduction zone on the left, Nankai, right? So subduction is going to the northwest here. The big megathrust events are outlined in yellow. There are long-term slow slip events shown here in the blue circles, and then the tremor appears to occur somewhat down dip of that. The conceptual model that's been developed would be, well, you have fluids being released by dehydration reactions, ascending. There's low permeability that occurs up in the serpentinized mantle wedge and possibly up dip from that. There's high pore pressures then, right? So you can see this plot of effective normal stress. It's entirely conceptual, right? But where fluids are being produced and possibly up dip from that, super high pore pressure, maybe approaching lithostatic, right? So the effective stresses and hence fault strength, the frictional strength would be really, really low. And many models require super low effective stresses in order to produce slow slip events. Okay, so the goal of this work really is to address these questions. Let's get quantitative, right? Take these calculations of fluid transport and figure out what is that distribution of pore pressure along major plate boundary faults. Super important because it controls the deviatoric stress levels in crust. That's what controls topography. It controls transmission of forces throughout the plate. Depending on what that absolute level of effective stress is, it tells you how sensitive the system will be to pressure changes from injection, for example, right? So very relevant to induced seismicity and the seismic swarms that accompany that. The magnitude of effective stress controls earthquake stress drops and slip. One of, when we model the big megathrust events, asking questions about ground shaking and tsunami hazard, we just simply adjust effective stress to obtain a very reasonable amount of slip, right? So it's in many ways, it's a tunable parameter and it shouldn't be. We need to think about really what are the processes that control it. And then as I showed you, that transition from friction to viscous is also, that which is in many models controls the depth extent of earthquakes. That's also controlled by pore fluid pressure. And so we'll tackle this question by doing steady state calculations where we'll build, extend the calculation I showed you before to not only look at fluid flux, but to turn that into pore pressure and effective stress. And so some of the, this shows three different, shows a model with three different parameter choices, and I'll take you through this in more detail for a subduction zone, right? So where did this come from? And I'll show you how different it is from the other model that I mentioned at the beginning, right, where pore pressure just continues to increase linearly with depth, right? That would be the black line. You get down to these depths of slow earthquakes, that's a gigapascal difference, right? So huge uncertainties here. We really, there's a problem that I think really needs attention. That's just a steady state calculation, but there's also dynamics of pore pressure, and then as well as fluid transport properties like porosity and permeability. And that's relevant because it's going to control how pressure perturbations get transmitted through the fluid, and that can affect slip. Is that slip going to be seismic, aseismic? For injection-induced seismicity, will you generate just a swarm of small events that are maybe just a nuisance or you don't even feel them, or will it trigger a large runaway rupture? Are there any precursors related to that pressure diffusion and slip process? Fault valving is another concept that comes up when we talk about dynamics of pore pressure, cycles of pressurization and then depressurization as fluid is discharged following earthquakes. And that's thought to be a really critically important process. It controls mineral solubility and is implicated in controlling gold and other mineral ore deposits. Just to illustrate some of the unsteady dynamics, right? These are two examples of seismic swarms. The one on the left is a naturally occurring seismic swarm that played out over a couple of years in Southern California, right? So it's labeled injection point. There's no actual, well that's injecting fluids, but some seal was breached. At least this is the conceptual model, and then the earthquakes migrated outwards over several years, over a depth range of several kilometers, right? So what's controlling that migration? Well, it's thought to be some pressure pulse propagating upwards through the system. The example on the right is a geothermal stimulation project in Australia about a decade ago. The event started near the injector and then migrated outward over time. So I think the injection lasted about 2 weeks, and the events migrated outwards for 2 to 3 weeks, right? So how do we take these observations, and these catalogs are getting really, really, high quality right now. And how do we use it to learn about the fluid pressure dynamics? And so we approach this not with just steady state calculations, but unsteady calculations where we integrate the modeling of frictional slip with pore pressure diffusion and permeability dynamics. I wanted to touch on geology real quick before presenting the results. So as I mentioned, there's huge evidence for cyclic pore pressures and fault valving in mineral deposits. So this is an example a couple hours to the east of where I live in the Sierra foothills, where these huge veins next to a steeply dipping reverse fault are formed. So these are quartz veins, and they're associated with gold deposits, right? So the presence of veins means that the fluid pressures have to episodically cycle, and sometimes they're going to exceed the minimum principal stress. And these are particularly common in rocks that have been exhumed from depths around the base of the seismogenic zone. In subduction zones, similar things are seen. So this is an example from the Alps. The plate interface was here, and this group was able to sample these rocks. They see really interesting vein sets, and then taking the orientation of these veins, they're able to figure out something about the state of stress and how it cycles. It is not a constant pore pressure. It's something that cycles episodically. And these authors, took these veins to provide evidence of near lithostatic fluid pressures. When you look closely at these veins, and they might be a couple centimeters thick, it's probably nearly impossible to see, but you'll see that they didn't open in one episode. They have what's called a cracked seal texture. So there's different increments of opening, each a couple, tens of microns. Right. So again, pointing to an intermittency in high fluid pressure, low fluid pressure, up and down. So we'll tackle this doing earthquake cycle simulations or earthquake sequence simulations. The first set of examples I'll show you come from a vertical strike slip fault, and it's just a 2D cross section. So this is really the simplest type of earthquake cycle model that you can set up. So the fault drops vertically downwards. It has velocity weakening friction in the upper part, velocity strengthening at depth. You take the two sides of this domain and just shear it at a constant rate. You call that the plate rate or the loading rate. The fault will slip intermittently. The first example I'll show just has a constant pore pressure, time independent, and hence constant effective stress. But the effective stress distribution is what's shown in red here. It does not increase linearly with depth. I'll later come back and tell you where this profile came from. But for now, we just take this, hold it fixed, and then we run the earthquake cycle simulation. And so here's how we often look at results from an earthquake cycle simulation. So we're modeling hundreds of years. This is just zooming in to 60 years. So this spans the whole slow loading, the interseismic period where there's not a lot going on, and then the big earthquakes. And we have to take adaptive time steps, right? We take long time steps during the interseismic period, short time steps during the earthquake. So I'll show you a number of these space time plots. So this is depth on the y-axis, time on the x-axis here. The colors are showing the log of slip velocity, right? So values above 1, that's an earthquake. The plate velocity is about a nanometer per second, and blue is basically locked, right? So as a function of time, most of the seismogenic time, the seismogenic zone sitting around not doing anything. So it's this dark blue color. There's an earthquake that happens here. If you look at it in time, right, it's just almost an infinitesimally thin vertical line, but you look at it at time steps, you can see what happened, right? The earthquake nucleated here at about 14, 15 kilometers depth, propagated up the fault, and then eventually ruptured through to the surface. During the interseismic period, in that velocity strengthening region, the fault is creeping, right? So think about the bottom of the fault creeping along, the top of the fault is locked, you're building up strain and stress concentration around this so-called locking depth. And so then it's natural that's where the earthquake nucleate. Sometimes we also plot results like this. So these are contours of cumulative slip. So at the bottom, these blue curves are every 1.5 years, right? So you can see it's fairly steady slip. the red contours are every second, right? So this is an earthquake. It nucleates here, and each second later, there's a little bit more slip, and you can see it spreading up the fault. So this is an earthquake cycle simulation, and it's, this one is in part of parameter space where we get periodic earthquakes. That's not necessarily always the case. So let's make it a little bit more interesting now. So I'll come back. The fault, in addition to being frictional, it's a fault zone of finite width, and it serves as a fluid pathway. We're only going to have vertical fluid flow, not fault normal fluid flow. And in this model, I'm just going to assume that whatever fluid source is below the model domain, so I'll just feed fluids in at a constant rate. So there is a solution to this problem where the fluids are just sending at that same input rate throughout, but you'll see that's not the case. Because there are these nonlinearities and different feedbacks, we'll get cyclic pressurization, depressurization, and this is known as fault valving. So fluids faults are well known to act as pathways for fluids. The fact that the fault has been slipping breaks the rocks and maintains porosity and permeability around the fault. And so the permeability is generally a lot higher around faults, especially in the fault damage zone, than in the surrounding country rock. And so we'll make the limiting case assumption that the country rock is impermeable, right? So then fluids simply ascend along the fault. There's no reason that pore pressure is spatially uniform across the fault, but there's a time scale, diffusion time over that fault zone width. And so if we're interested in modeling at time scales longer than that, then there's enough time for pressure to equilibrate in this horizontal direction, leaving only vertical variations in pressure. And so we'll work in that approximation, right? So then pressure obeys a diffusion equation. This is called the pressure diffusion equation, right? So it comes from just writing down conservation of fluid mass, assuming that the fluid in the pores are compressible and expand or contract in response to pressure changes, and then introducing Darcy's law. Fluid flows from high pressure to low pressure. K is the permeability. It's going to be one of the most important parameters in this study. Beta is the sum of pore and fluid compressibilities, and phi is the porosity. Their product is sometimes called the specific storage. So as I meant, we're going to assume, just for simplicity, that there's a depth-independent width to this damage zone. And I mentioned that we're going to neglect any horizontal variations in pore pressure. The transport properties here are not those of the fault core where slip is happening, but it's really dominated. This problem is really dominated by the properties of the damage zone, right? It just occupies more area, and that's where most of the fluid flow and pressure diffusion is happening. So think about this as damage zone permeability and storage. If you have fluids that ascend at some rate, right, in order to maintain flow, you need to have a pressure gradient that's greater than hydrostatic. And to understand, what controls that pressure distribution, we can come back to Darcy's law. This is the upward fluid flux, right? So it's just this term in brackets here. Fluids flow in response to pressure gradients in excess of hydrostatic gradient. And there's, this is the permeability and viscosity. So let's say that these properties are constant and the fluid flow is constant. So then we just integrate this to get pressure, and we get a linear pressure dependence. Right, so we have the usual hydrostatic term, but then to maintain upward flow, we need a higher pressure gradient. And the higher the pressure gradient is, the higher the fluid flux or Darcy velocity is. So that's the process that leads to overpressure. It's not nearly that simple because permeability and porosity are not constant. If you look at the pore scale like this and you imagine changing pore fluid pressure, right, you're going to dilate the pore, so the porosity will change, and then permeability is related to that, right? So that's going to change. Those are just elastic changes. The fault starts slipping, there's a stress concentration of the rupture front, it's going to crack the damage zone rocks, or it's going to open up connectivity there, right? So that process is going to increase permeability and porosity during slip. This is happening at depth. It's hot, there's water present, right? So there's active hydrothermal processes, precipitation of pore, silica and calcite and such that seals the pores and cracks. And that becomes increasingly important as you go to greater depths where temperatures are higher. You get deep enough, right? The rock matrix itself is viscoelastic. It can flow in response to deviatoric stresses, right? And you get those when the pore pressure and this confining stress are different, and you can get creep closure, right? It commonly happens in ice, where ice, seals up open pathways or moulins, right? Happens here in rocks too. So that's a process known as creep compaction, and unless you're pushing that fluid out, then that pressurizes the fluid. I've done work on that, and sometimes I present it as part of this type of talk, but I decided to focus on a couple other studies today, but we've looked into that as well. So we need to think about how permeability changes, and it's common to write down a Cassini-Kármán type relation that relates permeability to porosity with some power law relation. N equals 3 is a typical exponent here. And many modelers keep this reference permeability, K naught, and porosity, just keep these, treat them as constants, right? So any permeability change is attributed to a porosity change. But if we think about what that means, you can relate sort of relative permeability and relative porosity changes, and it's really only controlled by this exponent. Basically, if even an order of magnitude change in porosity, it's only an order of magnitude change in permeability. So it's actually not a huge change in permeability through this mechanism. I'll give you a couple examples that show evidence for vastly larger permeability changes. And the only way to get those is to change this prefactor K naught here. And that's the measure of the connectivity or the tortuosity of the pores. You can imagine, minerals, precipitating in the interseismic period, filling it in, and then once you start shearing that or slipping it, right, you break that. You don't change the porosity a lot, but you open up connectivity between the pores, right? And so that would be modeled by changing this prefactor K naught. Here are two examples showing huge permeability enhancement. So both of these are shallow injection experiments at a couple 100 meters depth that are both from Europe. One, which is really, and these are monitored with one or more boreholes and then instruments that sit around the fault. In this case, they were injecting into low permeability shale, and there's a 5-order, a permeability increase of 10 to the 5, right? It starts from a value of 10 to the minus 17 meters squared and increases by 10 to the 5, right? Massive change. Similar experiment done in carbonates, doesn't quite show that, but it's still 1 to 2 orders of magnitude permeability increase, right? So slip is clearly affecting permeability. It's not a surprise, right? But we're going to need to account for that through changes in this K naught. So we've introduced a really simple model for this. One component of the model is that there's a dependence on effective stress, right? As you start squeezing things closed or you start dropping the pore pressure, then so you increase effective stress, right? Then the permeability is reduced. So that's an elastic reduction. And we drop it down to some minimum value. This actually turns out not to be particularly important. Most of the dynamics are happening in this range. So that's the elastic dependence, and this sigma star parameter depends on the pore compressibility. The other, and this is where it gets a little or a lot ad hoc, is we need to introduce an evolution equation for this permeability. And this is where the structural changes in the connectivity take place. And so there's two processes we need to account for. When the fault slips, the permeability increases. So we're going to draw that permeability towards some maximum value via slip velocity. So this is saying that once you slip a distance L, then you've had significant permeability changes. If you think about shearing in a finite width shear zone, divide both of these, numerator and denominator, by that shear zone width. Numerator is a strain rate, denominator is some critical strain to get significant permeability enhancement. The other process is a healing or sealing process. This is, we typically think of this as that mineral precipitation. is one example of that. So there's a time scale over which that occurs, right? So it's a very minimal model, but I think it has a lot of value. The first set of simulations, I'll show you the original ones we did, just kept T, this healing time and this permeability enhancement distance, independent of depth. We later modified that in a second set of simulations where T now, the time scale decreases as you go to higher temperatures at depth. I think that's a lot more realistic. So if we go back to the steady state problem, but now we account for the elastic dependence of permeability on effective stress, and we go through that integration process again, now we get, we find that pressure originally starts out at the hydrostatic gradient, but then begins tracking the fault normal stress gradient such that effective stress becomes independent of depth. This is not a new result. It's something that Jim Rice pointed out in 30 years ago. So that was what we were using in that first simulation. As I mentioned, there's great geologic evidence for fault valving behavior, right? Where in the interseismic period, the fault seals, you get low permeability, the ascending fluids stall, they pressurize, they weaken the fault. It triggers an earthquake, and then that increases permeability, fluids can now discharge, and then the system depressurizes, right? And then that process repeats. So that's fault valving. And it comes out in our simulations as well, right? So now this is that same simulation I showed you before, but turning on the permeability and pressure dynamics. It's vastly more complex. What you see here is aseismic slip, this locking depth ascending. You see multiple active slip fronts propagating up near the base of the seismogenic zone. Eventually, these trigger, move into the seismogenic zone. Here, if we zoom in and look at versus time step, we can actually see a set of basically small earthquakes, like an earthquake swarm that ascends, initiates a larger event that ruptures the rest of the seismogenic zone. So really different behavior, and I'll show you this is controlled by fluid pressure dynamics. I think it's easiest to show in a movie. So this is those same space-time step plots of slip velocity. You'll see a vertical line up here that marks where we are in the simulation. These panels to the right show slip velocity in a linear scale, so you're really only going to see things during an earthquake. In a log scale here, so you can see the aseismic slip, you can see permeability, upward fluid flux, and then effective normal stress. We'll play this movie. Or not. Yeah, here we go. So you can see, the aseismic slip front is migrating upwards. That's coming, there's high fluid flux that's happening there, right? So the aseismic slip is causing an increase in permeability. That increase in permeability is allowing the influx of new fluids. They continue to pressurize that part of the fault, right? That weakens the fault and it helps drive further aseismic slip. You can see multiple of these pulses, they just get spontaneously generated. Some of them now, when it comes into the velocity weakening part of the fault, trigger the earthquake swarm. So while this is playing, I need to plug in my computer. I see something. Okay, so this is the swarm seismicity now. So the behavior is different whether, if you're deeper where it's less velocity weakening than near the surface where it's more velocity weakening. So this is fault valving. So we saw these interesting aseismic slip pulses that appeared to be coupled to and driven by these permeability changes and pressure changes. It's a pressure pulse ascending, weakening the fault, causing and driving this slip. Then the slip feeds back into the process. I'll show you another simulation. So what we did in this simulation, everything is the same except we reduced the healing time. And we started to see more of these aseismic, these fluid-driven aseismic slip pulses and pressure pulses that were occurring, right? So they started to occur somewhat periodically. And these interestingly enough, start to look like long-term slow slip events in subduction zones. This is a movie version of it. So you'll see these fault valving events occurring episodically. I'll note that in these simulations, the velocity strengthening transition is about 18 kilometer steps. So actually all of these events are happening in the velocity weakening region. And so at that time, this was several years ago now, we were like, okay, well, it's interesting that, the fluids are coupling in here clearly and promoting these events, but it still requires velocity weakening friction. And that turned out not to be true. So more recently, I've been working with Ozawa, postdoc in my group, to understand this. And rather than thinking about these more complex depth-dependent setups, we did a simpler setup, right? So just a planar fault, horizontal, so there's no gravity. We feed in fluids at a constant rate. The central part of the fault is allowed to slip unsteadily. The sides are driven at some constant velocity, right? So there's a steady state sliding, steady state flow solution to this. We can do linear stability analysis to see if it's stable or not, nonlinear simulations to see what the dynamics are if it is unstable. And we discovered this so-called, what we're calling now the fault valving instability, and it actually happens for a wide range of frictional parameters. So this example is with velocity strengthening friction. So you can see the same types of features that we saw in that more complex simulation, they play out in this idealized case, but even with velocity strengthening friction, right? So the weakening is really happening because the pressure is increasing, not because the friction coefficient is dropping. These events always occur and propagate in the direction of fluid flow. That's the unstable modes, and their recurrence interval and hence the slip per event. That's controlled by how quickly the permeability decreases, that permeability evolution timescale. There's a range of different behaviors that can be seen as we change the width of the fault relative to some length scales in the problem. So when the fault is very small, we don't have any unstable, no wavelengths are unstable. We just get steady sliding, steady flow. When, as we start increasing the fault size, now we start to get some unstable modes and we get these periodic events. This is a little bit longer fault, right? So becoming a bit more periodic. Another transition happens. This is an instability problem where there's a particular wavelength that has the fastest growth rate. That happens in a lot of instability problems like Rayleigh-Taylor and such. And so then that particular wavelength gets picked out and it leads to more pulse-like slip pulses. And this is an example for even larger fault, right? Now we're starting to get multiple active slip pulses on the fault at the same time, right? Simply because you can fit more of these unstable wavelengths within it. The linear stability analysis shows pretty clearly the conditions for stability. So the x-axis is that A minus B, so velocity strengthening to the right, velocity weakening to the left. This curve here is the stability boundary. On the y-axis is a non-dimensional parameter related to fluid flux and degree of permeability enhancement that controls sort of the how important this fault valving instability is. But you can see there's a wide region here in velocity weakening space where we get slow slip events. The colors are showing the growth rate of the instability from the linear stability analysis. The colors are showing the maximum slip velocity in one of these nonlinear simulations. So all the pieces fit together and are consistent. So I want to go back to the more complex simulations, and instead of doing this for a vertical strike slip fault, I'm going to do it for subduction zones. So here we did it for a 15-degree dipping fault in an elastic half space. Fluids again are confined to a fault zone, sort of fluid transport zone of constant width. They're going to be sourced at different depths. The ingredients to this model would be fluid flux. It's in this model inspired by petrology. So we have super low fluid flux. There's a step increase where there's a big dehydration reaction. And then that fluid flux can either continue on up the fault, or we do another variant on the model where we have a fluid sink. Think about when we get above that mantle wedge corner, what if the fluids are lost? they go up into the overriding plate, right? So then the fluid flux up the fault is reduced. So we play around with that. We use that same permeability evolution model that I showed you before. And so we get, these are steady state solutions of permeability with depth. We have depth dependent healing time. And so we turn to some lab experiments measuring the healing time scale of permeability as a function of temperature. You go to high temperatures, it heals really quick. So the healing time distribution with depth is shown in this black curve here. That's a big difference from the previous model. And then by solving this fluid, basically integrating Darcy's law together with the steady state version of this, we can obtain these distributions of effective stress. And so it's, hydrostatic gradient near the surface, and then you start to build overpressure. And then depending on the choices you make, you can kind of get different behaviors here. So let's take a look at these simulations. So this is a reference case. The fluids continue all the way up the fault. I'm plotting versus depth instead of distance down depth. So the velocity weakening strengthening transition is this top dashed line. The bottom dashed line is the depth of fluid release. And so there's this giant velocity weakening region here. And that's where all these slow slip events are happening. In the seismogenic zone, it's mostly locked. There's big megathrust events there. We have velocity strengthening near the surface, so we get some creep there. I don't think the solution, dynamics at depth are too sensitive to that. And then there's a lot of activity at the base of the seismogenic zone. Some of these slow slip events come up. They're building a stress concentration here, and you get a lot of smaller seismic events. And some of them sort of cascade upwards and over time and trigger megathrust events. So it starts to look a lot like real subduction zones. Let's do some variants, or actually we'll zoom in here so you can see a bit more detail of what's happening, right? So these events are happening every year, a couple per year, something like that. There's an interesting depth dependence to the recurrence interval. They happen more frequently at depth and less frequently shallower. And that's because we think of this depth dependent healing time, it's shorter at depth because it's hotter there than shallower. And that actually is very consistent with what's seen in many subduction zones. The longer term slow slip events tend to be up here, a little bit shallower. We can now start doing variants on this. So this example, we changed the permeability structure a little bit. We made it less permeable in the shallow part. So model A was the original model. Model C is the one I'm going to show you now. Because you have lower permeability near the surface, when you integrate downwards, you start to build overpressures quicker. So the effective stress is a lot lower. So model C it looks like model A, but just sort of shifted to the left. And so comparing those, A on the left, or C on the right, having lower effective stress, lower permeability kind of sharpens this up, right? In the model on the left, between the slow slip events, there's also aseismic creep. In the model on the right, that really doesn't happen, particularly in these deeper regions. So this shows you how that parameter affects things. The next thing we'll look at is motivated by, as I mentioned in Cascadia, there's possibly this transition region or gap between the currently locked zone and where slow slip is happening. What might cause that? So here's a careful geodetic inversion over the past, using data over the past 20 years, or at least 20 years before this study, that suggests partial coupling in that region. So that doesn't keep up with plate rate. So where does the extra deformation occur? Does it happen as part of a big megathrust event, right? Which then that rupture comes much more landward, stronger ground shaking for Seattle and Portland? Or does it slip aseismically just somewhat faster at some point in the cycle? So we were investigating the hypothesis, looking at what would happen if fluids, as they came up some distance above that mantle wedge corner, were diverted upwards. So we added a fluid sink here. So that drops the fluid flux. It leads to differences in effective stress. So lower pore pressure, higher effective stress, up dip from that fluid sink. Everything's pretty much the same below that. We compare these two models. The sink is shown here. What it did is it made the slow slip events below that. They still exist. They're more periodic now. It's in that kind of simpler part of parameter space. And it shut off the slow slip events up dip from that. And that, in many ways, looks very similar to what we see in Cascadia. What happens if we look over longer timescales, this is just zoomed in for 10 years, we see that the degree of aseismic slip here changes. Sometimes it's faster than the plate rate, sometimes it's slower. And so, right now Cascadia is late in the cycle, and this model predicts that late in the cycle, that aseismic slip rate would be below plate rate. So it looks pretty similar to what we see in Cascadia. Check the time. I think yeah, I have maybe a couple of slides on this. So I'm going to turn to swarm seismicity. We saw it in the original model, and we looked at it here in a pretty idealized setup. So here we're just injecting into a fault, and we do that with constant pressure boundary condition at this end. Pressurization is really confined to this slipped region because we have permeability enhancement from some super low value to a higher value. This model is more designed for injection-induced seismicity, so we ignore healing. It's happening over a much longer time scale than we're thinking about here. So we just have that permeability enhancement. And these are, these are really preliminary simulations. We did them kind of at a larger scale. We need to change the scales here, but focus on the solution behavior rather than the specific times. So it's known if the fault is velocity weak, velocity strengthening, you get aseismic slip in response to injection, and that the pressurization and the slip migrate out in a diffusive manner, distance growing as the square root of time. It is related to the hydraulic diffusivity, but it's not just a diffusion, pressure diffusion process. There's this prefactor that depends how close the fault is to failure, right? Because elastic stress transfer is also participating. So the plot on the left is showing pressurization expanding outwards. On the right, it's showing permeability increase expanding outwards. And there's basically sort of a crack edge or a rupture front migrating outwards. And so that migrates diffusively, but the slip inside this region is seismic and takes the form of swarm seismicity. A lot of the small events, at least for this part of parameter space, are concentrated close to the edge of that pressurized zone. There are larger events. This is now slip velocity, right? So then there are larger events, some of which nucleate back near the injector, some of which nucleate close to the leading edge of this slip front. So this looks a lot like, at least qualitatively, like some of those injection and either natural or injection-induced earthquake swarms. So this is another region, another problem area that we're working on. It depends on certain parameters. Here we just varied how close the fault was to failure by adjusting the initial shear stress. When you're in this highly understressed region, you tend to get a lot of small events near the leading edge. When the fault is close to critically stressed, then it's easier to slip and you tend to get these bigger events. So this may be, we're going to scale these up to these at higher resolution and look at the frequency magnitude distribution and the B value, which appears to be, it is used in induced seismicity studies to try to understand the dynamics. So I'll conclude here. Most of the talk was on slow slip, and I think this fault valving instability offers a compelling explanation for that. It does require frictional slip as the deformation mechanism. There are some other ideas out there related to unsteady viscous flow. It is, in contrast to many other mechanisms, actually fairly insensitive to whether the fault is velocity weakening or strengthening. It can happen at super low effective stresses or higher effective stresses. Some of the quantitative details change, but the qualitative do not. The recurrence interval and hence slip per event, it's really controlled by this healing time scale. And that might explain why you would get the depth variations that are observed. And then some subduction zones like Cascadia have somewhat periodic events, others have vastly more complex event. And there's a dimensionless parameter we've identified that appears to control that. this is a new model, right? And there's problems with it. The propagation rates we see are slower than what's observed, although we've now realized that if we make effective stress lower, and there's good evidence for that, then we get pretty fast migration rates. These events only go up dip, right, in the direction of fluid flow, at least for velocity strengthening friction. We need to do the 3D problem, and we have the code now working for that to understand a long strike propagation. I think there's going to be a lot of elastic stress transfer that does that. The fluids are ascending, or pressure is ascending upwards, and it might be somewhat misaligned, so then it starts slipping here and then migrates laterally. That's the conceptual idea. We'll see if it plays out in simulations. And then there's lots of things that we're thinking about working on. I'll just leave that list up here. Thank you, and I'll take your questions now.
And in a surprising turn of events, it looks like Torsten has a question.
Thanks, Eric. So there's these links between the pressure evolution and rate state friction, some of which are kind of trivial in the sense. Okay, cool. So in the sense that you have the normal stress and A minus B in your criteria is for H star. But then there are these other, I guess, more subtle things where you alluded to, you don't have to be velocity, whatever, strengthening to get the slow slip because you have the pressure dynamics now. And your permeability also has some sort of evolution law. So I wonder, if you could expand a little bit more on the parallels in the sense of thinking of pressure evolution as the equivalent of rate state friction, where it is an equivalent A minus B, and other regime diagrams where you get totally different dynamics. So for example, in one of your plots, you had lambda, right? And lambda does give you controls complexity, but then it has a different wavelength that's got nothing to do with the H star complexity.
Yeah, so Torsten's alluding to the standard explanation for slow slip events is that your velocity weakening at very low effective stresses, you're right near this sort of critical boundary where if the fault were larger, it would, or the nucleation link smaller, you would get earthquakes, but you're kind of in this really special region where you get slow slip events. A couple of differences between the model that are worth highlighting. This model, the modes in one direction, the direction of fluid flow, are unstable. With the standard rate state model, they're unstable in both directions. Our model, if we make it velocity weakening, it starts to morph between this fault valving instability into the standard rate state instability. And then intermediate to that, it kind of acquires characteristics of both. And in that case, you can get modes, unstable modes in both directions. I don't know, maybe subduction zones where we see some along, down dip propagation, maybe that's what's happening. Don't think we understand, well, we've done the linear stability analysis, but we need to kind of pick it apart a bit more before I can talk very intelligently about the different sort of nucleation links and such things involved.
And I guess,
but I will point out that the nucleation link for rate state friction is inversely proportional to effective stress. For the standard rate state model, it is independent of effective stress for the fault valving model. And that's a really important difference.
Yeah. And I mean, in phase space, could you think of sort of what a rate state spring slider would do? And then here's one that has the pore fluids, right? Because you have this evolution.
I mean, if you look at sort of shear stress and slip velocity, it probably traces out a nearly identical pathway. I don't think that's any different. Right, which also tells you that, the way the fault slips, how much slip per event, recurrence interval, you can tune either of these models to match the geophysical observations. And so I think the only way to discriminate between them, the best way is probably going to be looking at geology, the exhumed structures.
You look like Luke and then Sean.
Maybe also geochemistry, which can sometimes record evidence of isotope transport and such.
Yes, I have a more about the fluid migration problem. You you use this diffusive law, you know, that the dPdt equal the Laplacian of, you know, and how important is that, you know, what in this process that you have a diffusive process for this migration of fluid, because it's possible that migration of fluids occur on, you know, you speak about tortuosity and all this thing, but occurs along, you know, cracks and things like that instead of a porous media.
Yeah.
Is that going to change a lot of things? Or
It changes. Well, it is a pressure diffusion equation, but there's so many nonlinearities when you do the coupled problem that, you know, these unstable modes do not propagate diffusively. They're, you know, if it were pure diffusion, everything's damped out, right? Some of these modes are unstable, right? Because of these coupling. You know, the modes propagate like in the simulations, at least with uniform properties at a constant migration rate. That's not a diffusive like behavior at all.
it looks like a wave propagation.
It looks much more like a wave propagation.
Well, I'm
problem.
kind of confused. You know, you have a like an hyperbolic system, right, with elliptic value. You have an you know, a diffusion equation, and you get a transport problem.
Yeah, I don't know how to classify it in terms of hyperbolic or, right? I mean, it's got sort of it's got everything, right? You know, it's got a diffusion equation, so parabolic equation for pressure, but it's nonlinear. You've got static elasticity, which is like an elliptic problem with non-local elastic
Yeah,
stress
it's,
transfer.
yeah, it's a math problem. But the other question is, the core of the fault zone. Do you consider it elastic? Because through this dPdt, you know, it's kind of looks like bio or something like that, but it could be viscoelastic. It could have viscous behavior also inside the fault.
Yeah, so in the model I presented today, we only account for elastic porosity changes, and as part of what goes into that specific storage term, that dPdt term. In other models, we have dilatancy and creep compaction. So the matrix is viscoelastic plastic. So there are inelastic changes in porosity that are evolved, and they feed in as source terms that create either like suctions during dilatancy or pressurization during compaction.
So you have looked at that.
We've looked at that. Those models can also produce slow slip events, but they do not produce fault valving. At least in the model that we did, because we only had permeability depend on change because of porosity changes, and the porosity changes were really small. So the permeability didn't change very much.
So I'm interested in this fault width comment that you have there that is specifically, I guess, in the slow slip regime. Maybe I'll ask the kind of basic question. Why does it, when it's up dip of slow slip in the seismogenic, why does it always narrow back to a single plane? Why doesn't it just slip within the entire damage zone? And then the converse is, if you go down dip, why does it widen out?
In the seismogenic zone, there's a number of processes that promote that localization. So there's certainly all the fracturing and grain size reduction, but there's also thermal mechanisms. So when you know, the more localized the shearing is, the more heat you produce. The more heat you produce, you know, if there are fluids, well, when there are fluids present, you know, it can pressurize those fluids through thermal pressurization, and then that makes it weaker, right? And so that tends to localize things, and it's mitigated by pressure diffusion and thermal heat conduction. And that, you know, models like that predict localization down to the scale of hundreds microns.
And that's very much a fluid dependent.
That's one fluid dependent
Yeah.
localization mechanism. And I think then it's more of sort of the cataclastic processes that are also at play. And then you get fluids in there and they change, you know, there's reactions that promote growth of phyllosilicates and clays, and then those are weaker than whatever the host rock is. Right?
And why in the other direction do we go wide then?
I think it's that, at least for the power law rheologies, like dislocation creep, you know, you try to make it too narrow and accommodate the same sort of slip velocity being integrated viscous strain, right? And then your shear stresses, that flow stress becomes really high, right? So to make it, you know, the flow stress low enough that you actually can accommodate that deformation, the zone needs to widen. So the strain rates drop. So there's probably some feedbacks like that that are going on. We've also done earthquake cycle simulations with a viscoelastic bulk that touch on that question.
Great, thanks.
Question from Cakewall over here. It's a long distance throw.
Thanks for the interesting talk. So I'm simulating the fracture propagation and pressure evolution from multi-phase flow, and I'm using a similar permeability model. So I'm wondering, how do you choose your parameters in the model, such as the pressure sensitivity factor, because results are highly dependent on those parameters?
Yeah, in this model, right, so there's a couple of parameters, not a lot actually. There's some maximum permeability. That together with the assumed fault zone width and the fluid flux, that controls the overall extent of overpressure. And so we kind of select parameters so that the overpressure is such that the effective stress is in, kind of in the range of 100 megapascals. So we get the right stress drop during earthquakes, the right slip per event. There's actually, there is dependence on that stress sensitivity parameter. There's good lab experiments, lots of great lab experiments that constrain that. So I don't, in the results here, the dynamics are not qualitatively that sensitive to that. They're much more sensitive to permeability enhancement, that slip distance. They're also very dependent on the healing time, right? So the healing time, we turned to some experiments that looked at permeability reduction at different temperatures. More experimental work there would be fantastic. I think going back to the permeability enhancement, we're thinking about a model now looking at the stress concentration around the rupture front and thinking about how the damage zone, as the slip front goes by, how that damage zone material, whether or not you'd reach yielding conditions within it, and how much inelastic strain would accompany that, and then how that enhances permeability, right? And then that also is going to tell you how far off of the fault into the damage zone you are creating damage and enhancing permeability. So then that damage zone width becomes a dynamic parameter too. And so success there will depend a lot on, will depend a lot on having good lab data on how rocks yield in response to changing stress conditions and how the permeability changes in response to that.
Thank you.
Person, go for it.
People did this two-phase flow business. They found and got quite excited about these solitary solutions.
Yeah.
I wonder if you could get those, and given that then the speed would depend on the scale, on the amplitude, if that might explain some of the weird phenomena in the slow slip realm.
So this model does not have those porosity waves. The other model that we've done that has compaction and dilatancy does. It comes from the coupling between compaction and the pressure diffusion fluid transport equation. The porosity waves propagate a bit faster than the Darcy velocity, but not vastly faster than that. And so, in these models, that's 10 to the minus 9, 10 to the minus 8 meters per second, just many orders of magnitude slower than these events. So I've actually looked at the linearized dynamics of that equation. They are solutions, but they're not the relevant solutions. Yeah, exactly. So we looked at these equations without the coupling to slip, and they are solutions, but once you have the slip coupling, at least on these shorter timescales, that dominates the dynamics. It's not that compaction isn't important, but it just plays into the problem in a really different way.